Assalamualaikum warahmatullahi wabarakatuh. Here I will explain the article review. First of all, let me introduce myself. My name is Makaila Nuzula Azizi with student number 158. This article is entitled Progress in Nanomaterial-Driven Redox Reaction for Water Purification, a Critical Review, by the author Shahrukh Ali, Salim Badar, Daniel Alinika, Chua Siupen et al., and published in the journal Desalination and Water Treatment in the year 2024. In the next slide is table of content, purpose of the review article, introduction. Water pollution poses a significant global challenge that necessitates implementing effective remediation strategies. Redox reactions have garnered substantial attention in water treatment due to their capacity to disintegrate pollutants and eliminate contaminants. However, different catalysts may yield varying levels of efficiency necessitate diverse energy sources and entail different treatment duration for distinct types of pollutants. This review delves into the applications of metal oxide nanoparticles and hybrid materials in redox process for water purification. Iron oxide nanoparticles encompassing Fe and iron oxide nanoparticles have showcased remarkable efficiency in removing diverse dyes through photocatalysis and sonocatalysis. Cerium oxide and its composites have exhibited promising results in photocatalysis, sonocatalysis, and electrocatalysis, which can degrade the organic pollutants in water. Furthermore, hybrid materials like graphene-based nanocomposites have remarkably effectively eliminated color and heavy metals from contaminated water through redox reaction. The amalgamation of organic and inorganic materials in these hybrids augments their photocatalytic and antibacterial properties. Overall, the utilization of redox reaction and hybrid materials offer a promising approach to tackling water pollution and ensuring the availability of clean water. According to estimates, approximately 33% of the global population lacks access to safe and readily available drinking water service, primarily due to declining freshwater resources exacerbated by population growth. This situation has spurred the development of policies and procedures to prevent water pollution and establish wastewater treatment facilities. Human activities such as sewage discharge, industrial waste, and urbanization contribute significantly to water pollution, leading to ecosystem degradation and harm to aquatic organisms. The contamination of water bodies is particularly acute in developing countries, where untreated waste from various sources is discharged, posing sustainability challenges in the face of ongoing development. Various industries use chemicals and dyes, including leather, textile, cosmetics, and medical sectors, discharging Water containing these substances into water bodies can introduce toxic pollutants harmful to aquatic life. Additionally, industrial discharge of nitrates can cause severe health issues such as methemoglobinemia, commonly known as blue baby disease. Conventional wastewater treatment process aim to remove impurities like heavy metals, pathogens, dyes, and pharmaceutical through physical, chemical, or biological means or combination. There's there there sumpah habis 17. Redox reaction, fundamental to numerous chemical processes, involve change in the oxidation state of chemical species and comprise two-half reaction. In the oxidation-half reaction, the reactant undergoes electron loss, resulting in an increased oxidation number. Conversely, in the reduction-half reaction, the reactant gains electrons, which decrease its oxidation number. These reactions further oxidizing agents that facilitate oxidation by reducing themselves and reducing agents that promote reduction by being oxidized. Reactive oxygen species or ROS such as hydroxyl radicals, superoxide anions, hydroperoxyl radicals, and alkoxy radicals are frequently generated. ROS plays a crucial role in the degradation of pollutants through mechanisms including decomposition, disinfection, and adsorption. The utilization of zinc oxide in photocatalytic redox reaction for pollutant degradation. Aduh, salah. The picture in the slide explains about the second reaction is the reversible interconversion between. This section has discussed various techniques of water purification using redox process. The catalyst is critical in treating water and generates radicals in all procedures. There are three primary methods of generating radicals from the catalyst, which can be distinguished based on the technique used and can be augmented by different energy sources such as light or photocatalysis, high-intensity ultrasound or sonocatalysis, and electricity or electrocatalysis. Various metal oxide nanoparticle or NPS and their composites including zinc oxide, titanium oxide, and cerium oxide can also be used as catalysts in enhancing the generation of radicals. The first classification of redox reaction is oxidation mechanism of photocatalysis. Photocatalysis is a process in which a semiconductor or photocatalyst can be activated by light energy. This process leads to the formation of electron hole pairs or charge carriers through electronic excitation, such as the picture in this slide. Upon exposure to light, electrons move from the valence band to the conduction band in the photocatalyst, which reacts with oxygen to form superoxide anion and leave behind a hole in the valence band. These holes can then react with hydroxide anions. With a positive charge, the photocatalyst surface attracts electrons from water molecules in the air to produce, directly participating in oxidative degradation, the primary mechanism for production. Additionally, released electrons can react with dissolved oxygen in the water to generate, which subsequently break down to form hydroxyl radicals. Photogenerate reactive species including tulung salam sonatulung salam hapus. The second classification is role of pancake in photocatalytic activity. The knowledge and controlling the pancake is essential to develop efficient and effective photocatalytic system for environmental remediation applications. By modifying the pancake, researchers can design photocatalysts with improved activity, selectivity, and stability, paving the way for advanced water purification technologies and other environmental applications. The band gap size is a critical factor in determining the photocatalytic activity of semiconductor materials. Modifying the band gap enhances the efficiency of these materials in absorbing solar energy, which is fundamental for driving photocatalytic reactions. For instance, narrowing the band gap of metal oxides such as titanium oxide or zinc oxide can significantly improve their photocatalytic performance by enabling enhanced solar spectrum utilizations. A smaller band gap allows the material to absorb a broader range of visible light, thereby generating more electron-hole pairs that participate in redox reactions. In band gap engineering, doping enables the fine tuning of the electronic properties of photocatalysts. This fine tuning optimizes the generation of reactive oxygen species and improves the redox potential of photogenerate carriers. For example, doping titanium oxide with elements like gold and ruthenium has modified its band gap, enhancing this enhancing its photocatalytic activity under UV and visible light. A reduced band gap not only increases the absorption of visible light but also decreases the recombination rate of electron-hole pairs, thus enhancing the overall photocatalytic efficiency. The third classification is sonocatalysis process for water treatment. Sonocatalysis is a type of sonochemical process that involves activating a catalyst through ultrasonic radiation, creating liquid bubbles that rapidly expand and collapse, such as the image in this slide. This process produces several phenomena, including generating hot spots, sonolumin, sololumin, sonoluminescent. Please. And the last classification is electrocatalysis in a redox reaction. Electrocatalysis is an electrochemical process that involves redox reaction through the direct transfer of electrons. A voltage is applied across the electrode to balance the reaction potential, causing the electrons to move from a higher to a lower potential. Electrocatalysis is classified into two categories based on the material used in the electrode to generate radicals: direct electrocatalysis and indirect electrocatalysis, such as in the picture in this slide. Direct electrocatalysis can be used to produce radicals at the electrode surface without the use of any chemicals. One of the direct electrocatalysis methods is anodic oxidation, which can produce hydroxyl radicals from the water at the anode surface. The anode materials can be made from compounds such as apa itu kurang ngerti. The following section have evaluated various nanomaterials and their composite utilized by researchers in water remediation through Redox process. The first various type of nanoparticle is employment of zinc oxide in water remediation through Redox process. Zinc oxide occurs naturally in several crystal forms, such as wurtzite, zinc blende, and rock salt, and can be synthesized into various shapes, including spheres, rods, flowers, and discs. This versatility allows for tailored properties suitable for diverse applications. Zinc oxide has gained significant attention due to its varied morphology and the ability to modify optical, mechanical, electrical, magnetic, and chemical characteristics. Zinc oxide exhibits a broad and direct bandgap within the near UV spectral range, impressive oxidation capabilities, biocompatibility, environmental friend. The second various type of nanoparticle is employment of titanium dioxide as a catalyst in water treatment. Titanium dioxide, a naturally occurring compound, exists in three crystalline phases: anatase, rutile, and brochite. While the brochite form of titanium is challenging to produce in the laboratory, the production of anatase and rutile is more straightforward. Among these polymorphs, rutile is the most common and is chemically and thermodynamically stable. Over the past 40 years, numerous studies on titanium for water purification have demonstrated that it is the most efficient photocatalyst for water splitting, boasting outstanding photoelectrochemical capabilities due to its affordability, chemical stability, abundance on Earth, and non-toxicity. In photocatalysis, the anatase and rutile phases of titanium are commonly utilized as active agents owing to their chemical stability and resistance to photodegradation, although other semiconductors, like zinc oxide, have bandgaps similar to titanium dioxide and exhibit excellent photocatalytic characteristics. They are less favorable due to their lower photocatalytic stability and higher environmental toxicity. And this table in this slide explain about evaluated by the by researcher about employment of titanium dioxide as a catalyst in water treatment. And the third is application of iron oxide in the redox process. Iron oxide has emerged as a promising option in wastewater treatment due to its numerous benefits such as natural abundance, low synthetic cost, super paramagnetic characteristics, and environmentally friendly nature. It is available in various forms including magnetic, maghemite, hematite, and iron oxyhydroxide and metallic zero-valent iron. Although nanomaterials are generally challenging to recover from aqueous solution, the magnetic properties of iron oxide nanoparticles make them easily separable and recoverable from the solution. Several research studies have investigated the photocatalytic activity of iron oxide and PS, such as the table in this slide. And then is application of cerium oxide and their composite in redox process and water treatment. Cerium, a rare earth metal and the 25th most abundant element in the Earth's crust among 78 common elements, has gained significant attention in the field of catalysis. Cerium oxide stands out due to its biocompatibility, redox characteristic, transport qualities, thermal stability, oxygen storage capacity, and non-toxicity is catalytic application. It also presents a potential alternative to conventional photocatalysts such as titanium dioxide. Cerium oxide possesses several appealing attributes including the presence of MT4 orbitals that facilitate electron transfer, high stability in reaction environment, notable oxygen mobility resulting from the reversible transformation, and the ability to form a continuum of oxygen division. Non-stoichiometric numerous studies have been conducted to evaluate the efficacy of cerium oxide in water purification. And the last various types is application of hybrid material in the redox reaction for water remediation. Conventional ways of pollution control such as precipitation and biological approaches could lead to several complications including secondary contamination, excessive energy consumption, and system instability. Thus, the application of hybrid composites in redox reaction was suggested as part of the effort to alleviate these issues. Nanomaterials, including graphene and its derivatives, are widely employed in water treatment due to their large surface area and effective absorption capabilities. Scientists are developing graphene-based nanocomposites with improved photo-efficiency to break down contaminants and disinfect water. Capitalizing on graphene-based nanomaterials' remarkable photocatalytic and antibacterial properties. These hybrid nanomaterials, comprising multiple NPS, have exhibited remarkable efficiency in eliminating color and heavy metals, from polluted water, such as the picture in this slide of hybrid nanomaterial, and numerous studies have explored the utilization of redox reaction in water treatment using hybrid composites. Hybrid composite utilizing redox reaction hold the potential for their simultaneous removal of salts and contaminants in water treatment and desalination plants. Capa- Capacitive deionization, or CDE, is a desirable desalination method due to its low energy demand and environmentally friendly nature. Nevertheless, CDE present ion removal capacity falls short of practical use, mainly due to the constrained surface area of carbon electrodes for ion absorption. As a result, there is a requirement to develop a novel and cost-effective desalination technology that can achieve a high IRC. The picture explains about reaction mechanism under visible light irradiation and chromium 6 absorption. This picture explains about reduction mechanism of KDF. Kinetic degradation function is a hybrid material used in water purification. Conventional water treatment facilities often employ multi-layer filters to clean water, reduce turbidity, eliminate plankton, and remove odor. These filters typically consist of core layers of graded sand and supporting gravel. The efficiency of such filters can be improved by incorporating additional layers of KdF composed of high-purity copper and zinc particles in equal proportions. To enhance the effectiveness of multilayer filters in reducing chemical and biological contaminants in surface water treatment, KdF could be added to the multilayer filters. This KdF layer may consist of various ratio of copper and zinc granules, which can remove soluble contaminants and heavy metals such as lead, nickel, and iron. They also evaluated the capacity of the KdF to reduce the residual free chlorine concentration and certain biological species in water. And the other picture is um, mechanism of the enhanced photocatalytic bacterial activity of PAE on C3 and 4. This slide explains about pros and cons of the redox process. The redox process has been extensively utilized, studied, explored, and optimized due to its numerous applications. It is continuously improving compared to previous techniques as it offers a powerful